Okay, hello. Let's continue. So you can just for this group Dn, here n it's like 2, 3, 4, and on and on. For every integer, you get a group Dn. And you have the same kind of relations in Dn as you do for D4. So let me just summarize. Let me write the rules for Dn again at the top. Dn has two generators. A to the nth is the identity, B squared is the identity. And then in order to switch B and A, I replace A by A to the n minus 1. Okay, so you can prove the following formulas. B A to the j is just A to the n minus j times B. Let's see. Every element of Dn can be written A to the j, B to the L, j going from 1 up to n minus 1, L being 0 or 1. In particular, Dn has two n elements. B, A, B, A to the n minus 1b. And that is enough to, for us to figure out how to multiply it Dn well enough. Okay, so that's Dn. Okay, so for another example, which kind of has the same flavor, well, sort of, Q. Quaternions. Define Q to be the group generated by I and J, satisfying I to the fourth is J to the fourth is the identity. And I squared equals J squared equals IJ squared. Okay. Okay, so I've defined the quaternions using generators and relations. There's another way to present this group. So note, another way to define Q is by saying that it's a set plus or minus 1, plus or minus I, plus or minus j, plus or minus k, where ij equals minus ji equals k, and I squared, j squared, and k squared are all -1. And of course, implicitly, -1 kind of commutes with everything else. Can I read out this line?
No,
Oh,
so the line with number 3 on it. I can't see the little where A is and erase it to the power, and then you start with B and the last one.
Up here?
Yeah, by the A before the B. Before the B alone.
Oh, so this is supposed to be the identity, then A, then A squared, A cubed. Keep on going until you get to A to the n minus first power, A to the n minus 1. Now, A to the n is the identity, so it just repeats again. So don't put A to the n. And then you do B, AB. Basically, take all of these and multiply by B, and you get the other n elements.
Thank you.
Okay. Okay. Let me, sorry, my sound is weird. There we go. Okay. Now, I think that it is, I don't know, this way is more kind of like the usual way to define the quaternions, but it turns out to be equivalent to this way. Let me just explain for a tiny little bit how we might achieve, how we might show that this presentation is the same as this presentation. Okay, so let's call Q. Again, it's generated by I and J, two things. Okay. And let's let Z be I squared. Then Zi is just I squared I, which is just I cubed, which is just I squared, which is IZ. Also Zj, well, Z is I squared equals J squared. So Zj is just J squared J, which is just J cubed, which is just J squared, which is JZ. So Z commutes with I, Z commutes with J. So whatever combinations of I's and J's I write down, Z will commute with all of them. So if we put the center of Q just to be all the elements of Q such that Gx equals Xg for all X, then that means Z is in the center of Q. Okay. So this element I squared, also known as Z, commutes with everything in Q. And also Z squared is I squared squared is I to the fourth, which is the identity. So Z is a number whose square is 1. So that's why we call Z -1. Now notice there's a relationship between Ji and Ij, right? So Ij squared is Z. That means Ij equals Z. And so so multiply on the left by I, you get I squared J equals Iz. Multiply on the right by J, you get I squared Jij squared equals Izj. Now remembering that Iz equals Zi, we have Zij on the right-hand side. And on the left-hand side, this is Z, this is Z. We have Z, Ji, Z. In other words, now remembering that Iz is Zi and Jz is Zj, we have Z squared Ji equals Zij. In other words, Z canceling Z, we have Zji equals Ij.
Excuse, sir.
Or if I want to,
can you raise
yes.
the page, please? Thanks.
Yeah, I can.
Thank you.
Okay. Okay. So now we have, this gives us a rule on how to switch I and J. Like if you see Ji, well, multiplying by Z on both sides, you get Z squared, which is the identity. So it's Ji equals Zij. So now if you ever see J before I, you can switch them if you introduce a Z. Okay. And now you can write out all the elements of the group, right? Now Q, so basically every element of Q can be written I to some power basically what we want to say is we wanted to write it as either E, Z, you have I, Zi, You have J, Zj, and you have Ij and Zij. You just have 8 things. Okay. Right, and in some, as just an example, here's like some example of an element of Q. Might be like I cubed, J inverse, I to the 6, J squared, Ij. That's it. Okay. Here's just some combination of I's, J's, I inverses, and J inverses, multiplied all together in some order. Right? And we want to write it as one of these 8 things. Well, the strategy is to move all the I's to the left, all the J's to the right. And whenever we see a J squared or an I squared, we'll convert it to Z. And just remember that Z can be moved all the way to the left. Okay, so let's find all the Z's we can. So first of all, we'll do some scratch work. I cubed is Zi. J inverse, well, J to the 4th is the identity, so J inverse is really J cubed. I to the 6th is I squared cubed, so Z cubed. J squared is Z, and then we have an Ij. So let's substitute all this in here. So we have a Zi, we have a J cubed, we have Z cubed, we have J squared, which is Z, and we have Ij. Okay, now let's do more scratch work. J cubed is J squared J, which is Zj. So we have Zi 4th Ij. Now Z squared is the identity, so Z to the 4th is also the identity. And also Iz is Zi. So now we switch these two, we have Z squared Ij, Z to the 4th is the identity, Ij. And now this, remember that Ij squared is Z, and Z squared is the identity. So we have the identity times Ij squared, and Ij squared is Z. So this complicated thing just ended up being the element Z. So everything in Q can be written as a power of Z, a power of I, and a power of J, and each power can be 0 or 1. So every element of Q is like Z to the A, I to the B, J to the C, where A, B, and C are either 0 or 1. Okay, and that is, how we can compute with the quaternions, just as an example. So you see, like, now we have groups of order 8. We have a couple different ones. Okay. Let me tell you 2 of our other main sources of groups. Basically, we have groups coming from linear algebra also, and we have groups coming from like combinatorics as well. Okay. Let n be an integer. And let F be a field. For example, the real numbers, or even a finite field or complex numbers. I'll just put etc. Okay, then we define GL n of F to be the set of n by n matrices. Such that the AIJs are in the field and the determinant of this matrix is non-zero. In other words, the n by n invertible matrices over this field F. Then GLN F is called a general linear group Okay, it's a group. Well, group is in the name, but it's a group because we combine matrices by multiplying using matrix multiplication. The group operation is matrix multiplication the identity is just the identity matrix. Ones on the diagonal, zeros everywhere else. And the inverse of an element is just the inverse of the matrix, like how it normally is. The inverse of A is just A inverse, well, like regular matrix inverse. Okay. So it turns out part of linear algebra is just also group theory. And then a nice subgroup of GLN. We have the subgroup SLN to be those matrices A such that the determinant of A equals 1. This sits inside GLN. Oops. Okay. And we have this following proposition. If you define phi from GLN to SL, or sorry, from GLN to the real numbers, well, let's say like the non-zero elements of the field. Let me just write that down. F cross is Z in F such that Z is not equal to 0. And you define this by phi of A equals determinant of A. Then phi is a homomorphism. And the kernel of phi, well, that's the matrices of determinant 1, also known as special linear group. Okay. And that gives us a whole bunch more examples of groups. Well, we don't have much time to talk about it, but I mean, we'll talk a more about it later. But we can at least define it. Let n be greater than or equal to 1 be an integer. And then we have the symmetric group Sn, which is all the permutation sigma the functions from 1 up to n to 1 up to n such that sigma is a bijection. Okay. And this is a group. The group law is just composition of functions. I mean, I think we already did a few examples of this, but I'm officially introducing this as one of the things we're studying. Okay. The group law is by composition of functions. The identity of this group is just the identity function. And then, well, we need a little bit more time to talk about some of the special properties of Sn. So, more facts about Sn to come. And with that example, we now will have like a healthy stable of examples so that we can talk about, you know, interesting properties of groups and stuff like that. Oh, can I turn back 2 pages, please? Yes. Okay. But yeah, if you have a question, please tell me your question. But that's about it for me today. The page with SLN. I went too far back. Oh, you mean, so that's the same page. It was just at the top. And then the page before was GLN 1. And then before that, we have GLN, just the matrices with non-zero determinant. Okay, so yeah. Okay. Well, that is it for me today. Anyways, thank you all for coming out. And I will be posting an assignment today. So look out for that. Well, I'll post an announcement when I post the assignment. So I'll post the announcement of the assignment. Yeah, so that you'll know when it's there.